Okay, so this is workshop 3, part 6. We are on step 12, where we're about to apply Welch's method, or the p-Welch function in MATLAB, to our realistic time series that we generated. So we have in figure 3 and figure 4 already created power spectra for the realistic time series using the Fourier transform approach, so using the find PSD FFT function, and now we want to use Welch's method, which is a method which helps to reduce some of the variance in the output of the power spectrum. So in other words, to try and reduce some of this noisy background, the noise floor, which can inhibit us from identifying peaks in frequencies. So if we're reading, let's read step 12 then. So note that the Fourier transform approach for the more realistic time series in step 10 has a lot of variance, which makes it more difficult to identify peaks in frequency. A method that helps to reduce this variance, which is Welch's method, or the p-Welch function, divides the time series into short overlapping segments. Okay, and what Welch's method does is it divides into overlapping segments, windowed segments. So it will generate a power spectrum for each of the segments and then average them all together. And because each of the segments is going to have different random components, then when you're averaging a number of spectra with different random frequency components, actually the randomness tends to be sort of averaged out, and what remains are those frequencies which are consistent across all of those segments. So in other words, the periodic components that we're expecting to see. So p-Welch's method does all this for us. We just need to give it some inputs. So we've started transforming the find PSD p-Welch script into a function here, and we've written this first line at the top here. Now we just sort of glance through and we'll see that actually what we output, so our outputs here are PSDY2 and frequency 2. So I just need to make sure I assign these outputs at the top, PSDY2 and frequency 2. Okay, now because it's a function, we're passing it dt and y, so there's some things that it won't know unless they're defined within the function itself, or that we've passed to it. So we're passing it y, so we don't need to define y is equal to anything. We're defining n seg, I'll come back to what that is in a minute. Nw is a function of n and n seg. We don't have n. N is our window length, which is in our workspace, which actually my workspace has disappeared. Okay, well, it should be in our workspace. But I'm going to write it out here because our function will not know that n is actually supposed to be the length of our time series y. So n is equal to the length of the time series. We're defining nw as a combination of n and n seg. I'll come back to what this means in a minute. Okay, w defined based on nw. So we're all right with all of these things at the moment. The only other thing we haven't defined here is our sampling frequency, fs. So fs, sampling frequency, it's 1 divided by our sampling interval. Okay, so we've got our sampling frequency, we already know, is 10 samples per hour. Okay, I think we got everything there in order to run this. Let's just save that for the moment, and now I'll go back and explain what each of these inputs, what each of these variables do. So Welch's method divides the time series into a number of segments, and each segment is windowed to reduce leakage, and then each of those windowed segments is converted into frequency domain using a Fourier transform. So Welch's method uses Fourier transform as well. And then, because we've got a number of power spectra generated by each of the overlapping segments, we should mention that they're overlapped as well, then Welch's method averages all of those power spectra and thereby reducing some of the noise output. Okay, so let's just have a look at what I've defined here. So we've got the length of our time series, n. We have n seg is 5. So I'm just quite arbitrarily, really, suggesting that I want my time series to be divided up into segments that are the same length as 1/5 of the whole time series. Okay, so we want 5 segments, not 5 non-overlapping segments in terms that's how long it will be. Okay, so our window length then, NW is our window length, is then equal to the length of our time series divided by the number of segments. And then we're going to give it a window which is the same length as each of those segments. Okay, and I'm suggesting that we overlap each of those segments by a half of their length. Okay, now we get down here to the number of points to use in the fast Fourier transform. Now, normally it would be defined as the same number that you use in your time series, or to the nearest power of 2. Otherwise, it'll be padded with zeros until it is a power of 2. But I'm actually going to define it as being the same length as our window initially here. And when we call the p-Welch function, what we're passing it is our time series y and our window w and the number of points we want overlapped here. And n here, I really should put in n FFT, but I'm just going to leave it as n in order to so you can see the same figure that is in the instruction sheet, which has a higher resolution, but it's not, what should we say? It's not actually really resolved. It's a bit confusing, but I'll just generate it using n for the time being and then nw afterwards. Okay, so it will give us more data points in our power spectrum, but it doesn't actually improve our frequency resolution, so it's a little bit confusing to use a number of Fourier transform points that's longer than the time series, because it appears that you're getting better frequency resolution when you're not really. Okay, so we'll just try that approach and we'll run it and just have a look at the output. Okay, so save that, and then we want to type in PSDY, we might as well call it the same, PSDY2, frequency 2 is equal to find PSD underscore p-Welch, and then we are passing it dt and y1, which is our realistic time series. Okay, and we'll see if that works, and it does. Okay, so this output here is what hasn't got the same axes limits, but already if you look at the y-axis you can see that there's considerably more variance using the fast Fourier transform approach. Okay, so these are both power spectra that are generated from exactly the same time series, but the p-Welch method has treated it slightly differently in order to reduce the noise floor. And what we could do is we could actually plot this, the P-Welch method output, on top of the FFT method. If we go to figure 3 and we type in hold on, and then we could just use the same plot function here, except we'll so plot it down here, except we're going to make it pink, magenta. There. Okay, so you can see that by taking a number of segments and calculating the Fourier transform for each of those segments and then averaging them, we've reduced the variance considerably, which means that the true periodic components are much more visible above the background noise. So we've reduced the noise floor effectively. So just to sum up, what we've done in workshop 3 then is we've looked at artificial time series using sinusoids and then adding a noisy random component to make it a bit more realistic. And we've looked at 2 different methods for calculating spectra, one using the Fourier transform and one using Welch's method, or the P-Welch function. And what we have seen is that a problem that was observed in the real time series and in any time series, sorry, the initial time series, the one with purely periodic components, was that we observed a phenomena of leakage due to the truncating of the time series at the end. And we saw that by windowing the time series or tapering the ends of the time series, we effectively reduced the leakage, which is the observation of energy at other frequencies. Then when we've added noise to our time series, the power spectrum is also considerably noisy. And Welch's method helps to deal with that by dividing the time series up into segments and then averaging. So we've reduced leakage by windowing, and we've reduced noise by averaging over a certain number of segments. And that brings us to the end of this workshop.